Welcome to English for Professional Mechanical Engineers. My name is Jin Tu. I'm happy to have this chance to speak to you today about Computer-Aided Engineering, CAE. In today's lesson, we are going to introduce the second section of CAE, Finite Element Analysis. Let's get started. The finite element method, or FEM, is a numerical method for solving problems of engineering and mathematical physics. It is also referred to as a finite element analysis, or FEA. Analysis is performed based upon the law of mechanics. It covers solid and all structural mechanics, including dynamics, fluid mechanics, and thermodynamics. The process of analysis is divided as the physical problem given by design, development of a mechanical model, solution of the mechanical model, interpretation of result. The inner loop consists of refinement of analysis, improvement of model, while the outer loop including design improvement, change of physical problem. This cycle is iterated over many times, either manually or use the commercial optimized software. Typical problem areas of interest include structural analysis, heat transfer, fluid flow, mass transfer, and electromagnetic potential. The analytical solution of these problems generally require the solution to boundary value problems for partial differential equations. The finite element method formulation of the problem results in a system of algebraic equations. The method yields an approximation values of unknowns as discrete number of points over the domain. To solve the problem, it subdivided the large problems into smaller, simpler parts that are called finite elements. The simple equations that model these finite elements are then assembled into a larger system of equations that models the entire problem. As an example of how finite element model might be used to represent a complex geometric shape, consider the milling machine structure as shown. Since it is very difficult to find the exact response, like displacement and the stresses of the machine, under any specific cutting conditions, the structure is approximated as composed of several pieces in the finite element model. In general, there are several approaches to formulating finite element problems. First, direct approach. Second, variational method. Third, weighted residue method. For direct approach, in this method, direct physical reasoning is used as to preach element properties like characteristic matrices and vectors in terms of pattern variables. Although its applicability is limited simple types of elements, a study of this method enhanced our understanding of the physical interpretation of the finite element method. Finite element method use variational method. For example, Rayleigh method found the calculus of variation to approximate a solution by minimizing and associated error functions. In addition, the weighted residue method is a technique that can be used to obtain approximate solution to linear and nonlinear differential equations. If we use this method, the finite element equation can be derived directly from the governing differential equations of the problem without any need of knowing the calculus of variations. This method includes, for example, the collocation method, subdomain method, Galerkin method, and the least square method. In any given engineering problem, there are two sets of design parameters that influence the way in which a system behaves. There are those parameters that provide information regarding the natural behavior of a given system. These parameters include the material and the geometry properties, such as modulus of elasticity, thermal conductivity, viscosity, and the area moment of inertia. We illustrate some of the physical properties that define the natural characteristics of various problems, such as area, modulus of elasticity, area moment of inertia, shear modulus, and the polar area moment of inertia in solid mechanics example. Next, we define thermal conductivity and thickness in heat transfer example. And we define viscosity and roughness in fluid flow examples. Last, we define resistance and permeability in electrical and magnetic examples. Finally, we prepare some questions for you. Question 1. Which formulation is generally enhance our understanding of physical interpretation of the finite element methods? A. Direct approach. B. Variational method. C. Weighted residue method. C. Least squares method. Yes, the answer is A. Direct approach. Did you get it? Question 2. For the following parameters, which one is the most important in solid mechanics? A. Thermal conductivity. B. Viscosity. C. Modulus of elasticity. D. Permeability. Yes, the answer is C. Modulus of elasticity. So this is the end of this session, finite element analysis. I will see you again in next video. Goodbye.